Welcome back. Last episode we defined sequences and series, met the geometric, harmonic, and p-series families, and proved the divergence test. Today we build the working toolkit. Here is the central question of this entire half of the course. Given an infinite sum, the sum of a sub n, does it converge to a finite number, or doesn't it? Last episode we could answer this question only for very specific families. For a geometric series, we have a formula. For a p-series, we have a threshold. For the harmonic series, we have Oresme's grouping. But what if someone writes down the sum of n over 2 to the n? Or the sum of -1 to the n over n? Or the sum of 1 over the quantity n times the natural log of n? You need a procedure. Today we install 6 tests. The divergence test we already have. The integral test bridges sums and integrals. The comparison and limit comparison tests reduce unfamiliar series to known ones. The ratio and root tests examine how consecutive terms shrink. The alternating series test handles oscillating signs. We'll finish with absolute versus conditional convergence, the distinction that separates well-behaved from genuinely strange series, and a decision flowchart for which test to grab first. Let's go. Quick recap from last episode, because everything today builds on it. 3 families. The geometric series, the sum of r to the n, equals 1 over 1 minus r when the absolute value of r is less than 1 and diverges otherwise. The p-series, the sum of 1 over n to the p, converges if and only if p is greater than 1. The harmonic series is the p equals 1 boundary case. It diverges even though 1 over n approaches 0, and the divergence test. If the terms a sub n do not approach 0, the series diverges. That's a one-way street. If the terms do go to 0, the test is inconclusive. The series might converge, might not, you need a different tool. These 3 families and the divergence test are the benchmarks for everything we do today. The geometric series is what we'll compare to in the ratio test. The p-series is what we'll compare to in limit comparison. And the divergence test is the first thing you check, always. Now let's add to the toolkit. First new test, the integral test, statement. Suppose f is a positive, decreasing continuous function on the interval from 1 to infinity, and your series terms are samples of it, a sub n equaled f of n. Then the sum of a sub n converges if and only if the improper integral from 1 to infinity of f of x dx converges. The sum and the integral share a fate. They live or die together. Why? Picture the graph of f. Since f is decreasing, you can box it with rectangles of width 1. Use a sub n equals f of n as the height on the interval from n to n plus 1. These rectangles lie below the curve, so the sum from n equals 1 to infinity of a sub n is less than or equal to a sub 1 plus the integral from 1 to infinity of f of x dx. Use a sub n as the height on the interval from n minus 1 to n instead. These rectangles lie above the curve, so the integral from 1 to infinity of f of x dx is less than or equal to the sum from n equals 1 to infinity of a sub n. Sandwich the sum between 2 quantities that differ by a finite constant. If one is finite, so is the other. If one is infinite, so is the other. 2 caveats. The function must be positive and decreasing, otherwise the box argument breaks. So the integral test does not apply to alternating series, or to series whose terms bounce around. And the test tells you whether the series converges, not what it converges to. The integral's value almost never equals the sum's value. They merely agree on convergence. Beautiful test. It connects this episode to improper integrals from episode 8, and it has one immediate payoff. Immediate application. Let's use the integral test to prove the p-series rule we asserted last episode. Take f of x equals 1 over x to the p with p greater than 0. It's positive, it's decreasing, it's continuous on the interval from 1 to infinity. The integral test applies. We computed the improper integral from 1 to infinity of 1 over x to the p dx back in episode 8. It equals 1 over p minus 1 when p is greater than 1, and equals infinity when p is less than or equal to 1. By the integral test, the series, the sum of 1 over n to the p, converges if and only if the integral does, which is if and only if p is greater than 1. Done. The p-series rule proved. Specific case, p equals 2. The integral from 1 to infinity of 1 over x squared dx equals 1. So by the integral test sandwich, 1 is less than or equal to the sum of 1 over n squared, which is less than or equal to 1 plus 1, which is 2. The actual value is pi squared over 6, about 1.6449, which is indeed between 1 and 2. The integral test couldn't tell us pi squared over 6, but it confirmed convergence and bounded the value. Worth pausing on. The integral test is the only way in elementary calculus to prove the p-series threshold rigorously. Without it, you have the sum of 1 over n diverging, Oresme, and the sum of 1 over n squared converging, Basel, but no systematic story. With the integral test, the whole continuum p greater than 0 is settled in a single computation. Second test, the direct comparison test, statement. Suppose you have two series with non-negative terms, and term by term you have 0 is less than or equal to a sub n, which is less than or equal to b sub n. Then if the bigger series, the sum of b sub n, converges, so does the smaller, the sum of a sub n, by sandwich. And if the smaller, the sum of a sub n, diverges, so does the bigger, the sum of b sub n, because a divergent sum can't be bounded by a finite one. The picture is straightforward. Smaller positive terms can't add up to more than larger ones. Larger positive terms can't be bounded above by a divergent total. Strategy. The benchmarks, the series you compare to, are the geometric and the p-series. To prove convergence, bound above by a known convergent series. To prove divergence, bound below by a known divergent series. Quick example. Consider the sum of 1 over the quantity n squared plus n. Each term is at most 1 over n squared, because adding n to the denominator only makes the fraction smaller. So the sum of 1 over n squared plus n is less than or equal to the sum of 1 over n squared, which converges as a p-series with p equals 2. By direct comparison, the sum of 1 over n squared plus n converges too. Done. One caveat. Comparison only applies when both series have non-negative terms. If your series has signs, you'd compare the absolute value of the sub n to b sub n. We'll come back to that idea with absolute convergence later in the episode. Third test, the limit comparison test, a more forgiving cousin of direct comparison. Statement. For positive term series a sub n and b sub n, if the limit of a sub n over b sub n equals some finite positive L, then the two series share a fate. Why more useful than direct comparison? Direct comparison requires a clean term-by-term inequality, which can be a pain. Limit comparison only requires the same asymptotic order, same big O behavior. Pick b sub n to capture the leading order of a sub n. Take the ratio, check it's a finite positive limit, done. Example, the sum of the quantity 2n plus 5 over the quantity 3n cubed minus n plus 1. Ugly, but for large n, the numerator behaves like 2n and the denominator like 3n cubed, so the terms scale like 2 over 3n squared. Take b sub n equals 1 over n squared. The ratio s sub n over b sub n equals the quantity 2n plus 5 times n squared over 3n cubed minus n plus 1, which approaches 2/3 finite and positive. By limit comparison, the sum of a sub n converges, since the sum of 1 over n squared does. This is the test you reach for when terms are rational functions of n, or anything whose leading order behavior matches a p-series. Fourth test, and arguably the most, used in practice. The ratio test. Statement. Compute L, the limit of the absolute value of a sub n plus 1 over a sub n as n approaches infinity. If L is less than 1, the series converges, and in fact converges absolutely, a stronger property we'll define shortly. If L is greater than 1, the series diverges. If L equals 1, the test gives no information, and you need a different tool. The heuristic. The ratio test essentially asks, does this series eventually behave like a geometric series with ratio L? If the absolute value of a sub n plus 1 over a sub n approaches L less than 1, then for large n the terms shrink at least as fast as L to the n, an exponential, which is summable. If L is greater than 1, the terms eventually grow, so the divergence test kicks in. If L equals 1, the terms might shrink polynomially or stay constant. The ratio test is too crude to tell. When to use it? The ratio test shines on series involving factorials, exponentials, or powers of n multiplied together. Anything where the ratio a sub n plus 1 over a sub n simplifies cleanly. Example coming. And the limitation. On p-series, the absolute value of a sub n plus 1 over a sub n equals the quantity n over n plus 1 to the p, which approaches 1. The ratio test gives L equals 1 inconclusive for every p. So the ratio test is hopeless against the polynomial family. Use comparison or integral test there. Fifth test. The root test. Cauchy's test. Statement. Compute L, the limit of the nth root of the absolute value of a sub n. If L is less than 1, converges absolutely. If L is greater than 1, diverges. If L equals 1, inconclusive. Same verdicts as the ratio test. Same heuristic too. If the nth root of the absolute value of a sub n approaches L, then the absolute value of a sub n is approximately L to the n asymptotically. Geometric behavior with ratio. L below 1, it shrinks fast enough to sum, above 1 it grows, equal to 1 the test can't see what's happening. When to use the root test instead of the ratio test? Reach for it when your terms have an nth power structure, like a sub n equals stuff to the n. The root eats the outer power directly. Example, the sum of the quantity n over 2n plus 1 to the nth root gives n over 2n plus 1, which approaches 1/2 less than 1. Converges, 3 lines. The root test is technically stronger than the ratio test. There are series where root works but ratio gives L equals 1. But ratio is usually easier to compute, so most reach for ratio first. Root becomes the right tool when an nth power is visible. Sixth test. The alternating series test, also called the Leibniz test. Statement. Suppose your series has the form the sum of -1 to the n-1 times b sub n with b sub n greater than 0, so the signs alternate. If two conditions hold, b sub n monotonically decreasing and b sub n approaching 0, then the series converges. That's it, decreasing to 0. No need for the sum of b sub n itself to converge. Why does this work? Picture the partial sums. S sub 1 equals b sub 1. S sub 2 equals S sub 1 minus b sub 2, less than S sub 1. S sub 3 equals S sub 2 plus b sub 3, larger than S sub 2 but smaller than S sub 1, since b sub 3 is less than or equal to b sub 2. The partial sums bounce up and down, but each bounce is smaller than the previous. They're trapped in a shrinking window that closes to 0 width because b sub n approaches 0. They converge. Bonus, the error in truncating after n terms is bounded by b sub n plus 1, the size of the first omitted term, useful for numerical estimates. Canonical example. The alternating harmonic series, the sum of -1 to the n-1 over n, equals 1 minus 1/2 plus 1/3 minus 1/4, and so on. B sub n equals 1 over n is decreasing to 0, so this converges, even though the sum of 1 over n itself diverges. The sign flips save it. Actual value the natural log of 2, about 0.693. Now a critical distinction. Absolute versus conditional convergence. Let's say the sum of a sub n has terms with signs. There are two strengths of it, convergence. Strong sense, absolute convergence, not only does the sum of a sub n converge, but the sum of the absolute value of a sub n, the series of absolute values, also converges. Weak sense, conditional convergence, the series, the sum of a sub n, converges, but the sum of the absolute value of a sub n diverges. The convergence relies on cancellation between positive and negative terms. Key theorem, absolute convergence implies ordinary convergence. If the sum of the absolute value of a sub n converges, so does the sum of a sub n. You don't need the signs to save you. The converse is false. The alternating harmonic series, the sum of -1 to the n-1 over n, converges, but the sum of 1 over n diverges. So that's conditional convergence. The signs are doing all the work. Two quick examples to fix the distinction. The sum of -1 to the n over n squared. The absolute series is the sum of 1 over n squared. A p-series with p equals 2, greater than 1, converges. So the sum of -1 to the n over n squared converges absolutely. The sum of -1 to the n over n. The absolute series is the sum of 1 over n, the divergent harmonic. So the sum of -1 to the n over n converges only conditionally. Mnemonic. Absolute convergence is robust. The sum is well defined regardless of how you order or sign the terms. Conditional convergence is fragile, depending entirely on delicate cancellation. The next slide makes fragile precise. Riemann's rearrangement theorem. One of the most bizarre results in elementary analysis. Statement. If the sum of a sub n converges conditionally, then for any target value L, including plus or minus infinity, you can rearrange the terms of the series so that the new sum equals L. Let that sink in. The alternating harmonic series sums to the natural log of 2 about 0.693 in the standard order. But by reordering the same terms, using exactly the same numbers with exactly the same signs, you can make it sum to pi or 42 or minus 1 million or plus infinity. Same terms, different order, different sum. Why? Because, in a conditionally convergent series, the positive terms alone sum to plus infinity and the negatives to minus infinity. You have infinite reservoir on each side. To target L, add positives until you exceed L, then negatives until you fall below. Repeat. Each adjustment is smaller because individual terms go to 0. The partial sums converge to L. Contrast. Dirichlet proved that absolutely convergent series sum to the same value under every rearrangement. That is the deep reason absolute convergence is the real notion of convergence. The sum is independent of order, the way finite sums are. Conditional convergence is fragile by comparison. Move the terms, get a different number. First worked example. The integral test on the sum of 1 over n squared. Step 1. Check hypotheses. The function f of x equals 1 over x squared is positive on the interval from 1 to infinity. It's decreasing because its derivative, minus 2 over x cubed, is negative, and it's continuous everywhere except x equals 0, which is outside our interval. All conditions met. Step 2. Compute the improper integral. The integral from 1 to infinity of dx over x squared. The antiderivative is minus 1 over x. Evaluate from 1 to infinity. At infinity, minus 1 over x approaches 0. At 1, minus 1 over x equals minus 1. Subtract 0 minus the quantity minus 1, which is 1. Finite. Step 3. Conclude. Since the integral is finite, by the integral test the series converges. Done. Bonus. We also get bounds on the value by the sandwich. The integral test gives the integral from 1 to infinity of 1 over x squared dx is less than or equal to the sum of 1 over n squared, which is less than or equal to 1 plus the integral from 1 to infinity of 1 over x squared dx, so the sum is between 1 and 2. The actual value, by Euler's-Basel computation, is pi squared over 6, about 1.6449, indeed between 1 and 2. The integral test couldn't find pi squared over 6, but it confirmed convergence and gave a reasonable window. This is the canonical first example of the integral test. Second worked example, the ratio test on the sum of n over 2 to the n, which we previewed earlier. Now let's do it cleanly. Set up the ratio. A sub n plus 1 over a sub n equals the quantity n plus 1 over 2 to the n plus 1 divided by n over 2 to the n. The factor of 2 to the n over 2 to the n plus 1 becomes 1/2. The quantity n plus 1 over n stays, so the ratio is the quantity n plus 1 over n times 1/2. Take the limit. The quantity n plus 1 over n equals 1 plus 1 over n, which approaches 1 as n approaches infinity, so L equals 1 times 1/2, which is 1/2. Decision. L equals 1/2, less than 1, so by the ratio test, the sum of n over 2 to the n converges absolutely. The absolute convergence is automatic since the terms are positive. The sum of the absolute value of a sub n equals the sum of a sub n, but the ratio test always gives you absolute convergence as a bonus. Why was the ratio test the right tool? Because each term has an exponential 1 over 2 to the n factor, and consecutive terms simplify cleanly. The 2 to the n cancels nicely. Whenever you see factorials, exponentials, or products of powers of n, try the ratio test first. Third worked example, and a great one, the alternating harmonic series. The sum from n equals 1 to infinity of -1 to the n minus 1 over n equals 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5, and so on. Apply the alternating series test. Write the series as the sum of -1 to the n minus 1 times b sub n, with b sub n equals 1 over n. Check the conditions. B sub n equals 1 over n is positive, yes. It's decreasing. 1 over n plus 1 is less than 1 over n, yes. And b sub n approaches 0, yes. All three hypotheses met. By the alternating series test, the series converges. The actual value for the record is the natural log of 2, about 0.693, by plugging x equals 1 into the Taylor series for the natural log of 1 plus x, which we'll properly derive next episode. Now check absolute convergence. The series of absolute values is the sum of 1 over n, the harmonic series, which diverges. So the alternating harmonic series converges, but the sum of the absolute value of a sub n diverges. By definition, the series converges conditionally, not absolutely. Putting it all together, the alternating harmonic series is the canonical example of conditional convergence. And by Riemann's rearrangement theorem, you can reorder its terms to make it sum to anything you want. Sums to the natural log of 2 in the natural order. Reorder, and it sums to whatever you want. Same terms, different value. Strange. The flowchart. Given an arbitrary series, the sum of a sub n, which test do you reach for first? Decision 1. Does a sub n approach 0? Compute the limit of the terms. If no, you're done immediately. Divergence test, series diverges. If yes, proceed. Decision 2. Is this a known family? Is it a geometric series with the absolute value of r less than 1? Is it a p-series? If yes, you have a formula or a threshold. Use it directly. If no, proceed. Decision 3. Is it alternating? If yes, try the alternating series test. Check decreasing and going to 0. If those hold, converges, possibly conditionally. If no, proceed. Decision 4. Does the expression contain factorials, exponentials, or products of powers of n? If yes, reach for the ratio test. It's almost always the right tool. If the ratio test produces L equals 1, fall back to the root test or comparison. If no factorials or exponentials, proceed. Decision 5. Is the series positive and does it asymptotically resemble a known series? If yes, use limit comparison. Pick the known series as your benchmark. Direct comparison if the bound is easy. If you can't find a clean comparison, fall through. Last resort, the integral test. Identify f of x with a sub n equals f of n. Check positive, decreasing, continuous. Compute the improper integral. That's the workflow. 5 decisions, 6 destinations, most series exit within 2 or 3 steps. The flowchart is your friend. 6 pitfalls. 1. L equals 1 in the ratio or root test means inconclusive, not converges. Students see L less than or equal to 1 written in their notes and assume it means convergence. It does not. L less than 1 converges, L equals 1 tells you nothing, you need a different test. 2. The comparison tests, both direct and limit, require non-negative terms. If your series has signs, you compare the absolute value of a sub n to a benchmark instead, which detects absolute convergence. From there, the absolute convergence theorem upgrades to ordinary convergence. 3. The alternating series test needs both hypotheses, b sub n decreasing and b sub n approaching 0. Just going to 0 is not enough. A counterexample, b sub n equals 1 over n for n even, 1 over n squared for n odd, goes to 0 but isn't monotone, and the alternating series could diverge. Always verify monotonicity. 4. Conditional convergence and absolute convergence are different beasts. If you need to rearrange a series, take limits inside sums, or do anything fancy, absolute convergence is what you want. Conditional convergence is fragile and breaks under manipulation, courtesy of Riemann. 5. The integral test certifies whether the series converges, not what it converges to. The integral's value and the series value are different numbers. They just happen to be finite or infinite together. Don't confuse the two. 6. The eternal reminder. The divergence test can only prove divergence. If a sub n approaches 0, the divergence test alone gives no information. You need another tool, always. Recap: 7 tools. Integral test. If f is positive, decreasing, continuous, and a sub n equals f of n, then the sum of a sub n converges if and only if the integral from 1 to infinity of f dx converges. Use this to prove the p-series rule as a corollary. Direct comparison. If 0 is less than or equal to a sub n, which is less than or equal to b sub n, then convergence of the sum of b sub n implies convergence of the sum of a sub n, and divergence of the sum of a sub n implies divergence of the sum of b sub n. Limit comparison. If a sub n over b sub n approaches L with L between 0 and infinity, then the sum of a sub n and the sum of b sub n share fate, useful for rational function terms. Ratio test. L equals the limit of the absolute value of a sub n plus 1 over a sub n. L less than 1 converges absolutely, L greater than 1 diverges, L equals 1 inconclusive. The workhorse for factorials and exponentials. Root test. L equals the limit of the nth root of the absolute value of a sub n, same verdicts as the ratio test, best when an nth power sits in the term. Alternating series test. The sum of -1 to the n minus 1 times b sub n, with b sub n decreasing to 0, converges. Absolute versus conditional. The sum of the absolute value of a sub n converging implies the sum of a sub n converges absolutely. If the sum of a sub n converges, but the sum of the absolute value of a sub n diverges, conditional convergence. Riemann, conditional series can be rearranged to sum to anything. 7 tests, 1 flowchart. Next episode, we put them to work on the greatest application of series in calculus, Taylor and Maclaurin expansions. Functions as infinite polynomials. See you there. That's the Convergence toolkit. 7 tests, a flowchart, and the absolute versus conditional distinction with Riemann's theorem to highlight how strange conditional convergence really is. If this helped, like, subscribe, comment. Drop your favorite hard-to-classify infinite series in the comments. Bonus points if the ratio test fails. That's where it gets interesting. Next episode, Taylor and Maclaurin series. With the Convergence toolkit in hand, we'll finally represent functions like e to the x, sine x, cosine x, the natural log of 1 plus x, as infinite polynomials. The whole point of building this machinery was to make sense of those representations. Coming next, see you there. Convergence tests are the working machinery of the second half of calculus. Last episode, we defined what a series is and met 3 families: geometric, harmonic, p-series. Today we built the procedural toolkit. The integral test connects the sum an to ntf of x dx and proves the p-series rule as a corollary. Comparison and limit comparison let you reduce an unfamiliar series to a known one. The ratio and root tests look at consecutive ratios or nth roots and give a verdict whenever those limits are not exactly 1. The alternating series test handles series whose signs oscillate. Absolute versus conditional convergence separates the well-behaved series from the dangerous ones, the conditional ones, where Riemann's theorem says you can rearrange the terms to sum to anything. Next episode, we put this toolkit to work on the greatest application of series in calculus, Taylor and Maclaurin expansions, where we represent functions like e to the x, sine x, cosine x as infinite polynomials. We'll need every one of these tests to figure out where those polynomials actually converge. Subscribe so you catch it. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.